The first practice problem in section 5.4 on power is I've copied it right here into my notebook. And just a couple of things about my notebook. Notice I have a header at the top of this page describing what it is that I'm doing with a date. And I'm working practice problems from this section. And this is the first problem. And I just want to make the point that this took me 2 minutes to copy out of the book, which is not nothing. I get that 2 minutes of copying is 2 minutes of copying, but you get value out of having the actual problem written in your notebook, because if you come to if you have an issue or you get the wrong answer or you get stuck and you don't know how to continue, then all the information is right here so that you can share that with a partner or your teacher or a tutor or anyone else who might be helping you work through these problems if you do need that help. So part of the discipline of working problems is communicating what problem you're actually working, which I've done here. And I'm going to begin, let's just read it. A 1,000 kilogram elevator carries a maximum load of 800 kilograms. And there's a constant frictional force of 4,000 newtons that retards the elevator's motion upwards. In other words, working against the motion of the elevator as friction does. What's the minimum power in kilowatts that the motor must deliver in order to lift this fully loaded elevator at a constant speed? So I'm going to begin by just collecting the things that I know that are given to me. And when I do that, I'll just say mass of the elevator. I use a little subscript E, and I'm going to copy it exactly as it's given to me in scientific notation so that I preserve the significant digits, the two significant digits in this problem. Now, the mass of the elevator load, I just call that M sub L, is 800.0 kilograms, 4 significant digits. And we have a force of friction that is working against our motion, and that is 4,000 newtons. Again, I'm going to keep it in scientific notation to preserve the two significant digits. And that's working against the elevator's motion upward. What minimum power in kilowatts must the motor deliver if it's going to maintain a constant speed of 3 meters per second? So let me write that down. We got 3.00 meters per second, and we're looking for power. And we're told to report our answer in kilowatts. And another point that I want to make about just what I've done so far, aside from preserving the significant digits in each of my quantities and writing the units, this is a mass, so I use M to represent it. The subscript gives me more information about the mass. It's not E sub M. It's M sub E, because it's first of all a mass, and it happens to be the mass of the elevator. This is a mass that represents the load in the elevator. Same here. This is not friction force. This is force of friction. The capital F indicates that this is a force. That corresponds with this unit, newtons. The little f indicates that it's the force of friction. And then, so the subscripts give us more information about the quantities, but make no mistake, M is for mass, F is for force, V is for velocity or speed, and capital P is for power. All right, so, we got a lot of information here, and I'm going to try to make sense out of it by drawing a little diagram. Really simple. Here's my elevator, and I know that there's some force acting in this direction, and it's M times G. Notice I didn't specify what M. It's going to be the total mass, the sum of these two together, but I'll just leave it there as the combined mass times G, the acceleration due to gravity. Maybe I'll add that to my list too. Notice, when I put G on the list of knowns, 9.81, and that's meters per second squared. This is the acceleration due to gravity. It has units of acceleration. All of my quantities are using SI units except for power. I'm going to ultimately have to go from watts to kilowatts to report my answer appropriately. But when you write something, write the number and the units. It's not 9.81. It's 9.81 meters per second squared. All right. Let's imagine that the elevator is moving this way. It's going up with a speed of v. Okay? There's also going to be a frictional force, and I'll just draw that here, acting in this direction. So in order for this elevator to lift both the friction, the weight of the elevator and its load, it's going to have to also work against this force. So the force that the motor has to supply is going to be the sum of these two forces. And so that's what the most important thing that we get out of this diagram is we are asked about what this motor is doing that's supplying this force that's lifting this whole elevator. And so that is the force that I need to consider in my power calculation because I'm asked about the power that the motor has to exert. And so this all is getting us towards our formulas now. And we have two formulas here for power. This one, power equals work over time, and this one over here, power equals force times velocity. And if you look through section 5.4, you'll notice that they're really the same formula. But in this problem, I want this relationship. The force, the power is equal to the force times the velocity. And the reason is because I'm not told that a certain amount of work is done. I'm not told that there's a force acting over a particular distance and we're doing that for a particular time. I'm given a velocity that we're trying to achieve with this elevator, and that comes right into this equation. And to be clear, maybe I can fix my formula a little bit. I'm interested in the power that the motor has to exert, which means I'm also interested in the force that the motor has to exert. So let's keep going here. I know that in my solution the force of the motor is going to be equal to the mass times the acceleration due to gravity plus the force of friction. Okay, because the motor force is going to have to overcome both of those things, times the velocity. And I'll continue by expanding this and adding in the two masses that I'm using here. Watch how I do it. I'm not plugging numbers in yet. I'm going to take my elevator mass and the load. I'm going to multiply that by g after adding them together. Then add the force of friction, then multiply the whole thing by v. And so when I actually work this problem out, or when I substitute, I've got the thing I'm looking for on one side, and then everything else that I know is over here. Mass of the elevator, I'm going to just write it all in standard notation, 1,000 kilograms plus 800.0 kilograms times 9.81 meters per second squared, plus the force of friction, which is 4,000 newtons, and that whole thing times the velocity, which is 3.00 meters per second. And let's see what we get from the calculator. The value of doing all this work over here is that now I can very quickly just plug into my calculator 1,000 plus 800 times 9.81 plus 4,000, and I'm multiplying that whole thing by 3. And I get 64,974. And as you know, I'm really only allowed two significant digits in this calculation. And so I'm going to round this number to 65,000. And that is watts, because that is the SI unit. And so if I want to convert to kilowatts, I want to know how many thousands of watts I have. I have 65,000 watts, which is 65 kilowatts.